Okay, thank you. Hi everyone. This is a work in cooperation with Artesia, Franz Schaas, who couldn't be here, and we're grateful to Dunea Water Management Company in the Netherlands that allowed sharing these results with you. So this is a very complex area in the Netherlands, and they have a lot of ancillary information, very good ancillary information. So it's a managed aquifer recharge system, infiltration in the dunes, and pumping for drinking water purposes. Then you got issues, obviously, of monitoring of salt groundwater, complex geology, and you also have external dunes. This is called the sand engine that they built just in front of their wells, basically, to try to stop the saltwater intrusion coming in. This is an area where they've been working on for a very long time, so we have a wealth of information, and on top of it, they decided flying some Airborne EM. So that was a SkyTem survey in 2011, 2 areas. I'm going to focus just on the one in the south. Everything was inverted with Oral's workbench, fairly close line spacing. It was flown both out in the ocean and inland. And one of the main goals of the survey is mapping the saltwater intrusion. Where is it now? And how did it progress inland over the last 10 years? Has it progressed at all? Okay, so the approach of this study was begin by studying the ancillary information present. You don't want to fly something if you are not sure that it can actually do something useful for your problem. And in order to do that, you need to study ancillary information. Then it was flown, then we processed and inverted the entire data set without any a priori. We just kept it there in the drawer. Then we compared the results against the a priori, and then we found, obviously, that a priori could actually help in refining the inversions further. So we found these strategies to make best use of the a priori in the inversion. We ran these refined inversion, and then while we do that, you can also test different possible alternative scenarios from a hydrogeological standpoint. This is some of the ancillary data they have. This is an old map, but still, you get a feel for the amount of quality of information that they have. This is high density. This is the Holocene clay layer. I'll talk a bit about that later. So it's a very flat and constant elevation layer, very important feature in what we'll be talking about later. And basically the idea is that you have the salt water wedging in from the ocean, sort of sliding on top of this clay layer. And it doesn't go down, but it does continue here. They have a number of, as I said, different types of data sources. This is water quality. And basically, wherever you see gaps in these vertical profiles, is that because you got clay. So you obviously can't extract water quality from clay. So basically you can say that everywhere above these clay layers, you got this wedge of saline water coming in, not everywhere, but in places. And the question is, can we use Airborne EM to map this interface better? They also had so-called salt watchers. They're basically in situ resistivity monitoring systems that can measure resistivity continuously. This is a series of resistivities measured over 18 years or something, and very, very useful for comparing our results against. So they actually, even though they're called salt watchers, they actually measure resistivity. And it's actually the formation resistivity. These are some of the cone penetrating tests data, and basically wherever you see those darker intervals, that's where you have the clays. And this is an elevation, so you can say, obviously this doesn't have any spatial meaning, it's just all the drilling put side by side in alphabetical order. But what's interesting is that you can say a very continuous, distinct clay layer present pretty much everywhere. It's those Holocene clays. Okay, so after it was flown, then we process it and invert it without a priori. And obviously, there was issues of ambiguities in results, so we like to scan our model space and regularization space at length. So we ran both few and multi-layer inversions, smooth and sharp inversions, always without a priori. I mean, you see in here the clay from the geological model, but it wasn't used. In these realizations, it wasn't used. Okay, so smooth multi-layer model, few layer blocky model. I'm not going to go into details, but basically they give complementary information, and we'll use everything we have. I'm going to show you the results of a smooth inversion, which we tend to use the most in this case, and we're going to slice through different elevations. So this is where we have descent engine here, and we're just above above sea level in there. These are conductivity scales, so red conductive. And then we slice through, and you can see the salt front coming in at different elevations. It's not, it doesn't progress parallel to the coast always at the same rate. And we're minus 16 meters, minus 20, minus 30, minus 40, minus 50, minus 80. And out here we start losing some models, and this is because the models have been clipped with a depth of investigation. So it's fairly shallow out here. It's not like we're seeing through 100 meters of ocean. It's just 5 or 10 meters, so we're seeing through into the sediments that deep. Anyway, onto a cross-section, again without any a priori. So this cross-section sits there, and this is basically what we see. This is reversed east-west, so that's the ocean there. These are the dunes. Now you can clearly see the salt water coming in down here in this cross-section. Then France did something very interesting. So he drew some more cross-sections and he overlaid on top of them not just the clay layers. So in black you have the clay layers from the compenetrating test. He also overlaid on top of it resistivities from the salt watchers. So in the background you have the Airborne derived resistivity, in the forefront the resistivity measured in situ by these salt watchers, and we are on the same color scale. And basically they agree very well, I would say. You also get a feel, of course, that there is something happening close to the clays, to the shallower clays. This is another cross-section in there. Again, look at these, how well you map these. Again, you know, there is a clay, there is something slightly more conductive above the clay. Is it the clay, or is it actually the salt water wedging above the clay? Pretty hard to tell at this stage. Another cross-section. This is one of the clearest. Again, look at how well these interfaces are picked. And we're spanning fair range of resistivity. We're going from 1 to close to 100 ohm meters in more bluer bit, and actually matches well. These are all cross sections. You can see them here perpendicular to coast. And this is my favorite graph from a geophysical perspective. So in here, again, no spatial meaning of anything in here. It's just all the ancillary information available, ordered in alphabetical order. You have it in the forefront, and in the back it's compared against the Airborne derived resistivity. So in the background, Airborne derived resistivity, in the forefront, clays in black, and resistivities from salt watchers. These was taken from the sounding closest to the ancillary information. Of course, I think we are within 30 meters. And yeah, I mean, look at this. We're actually picking, wherever you got resistivities, there are very few places where you've got outliers, perhaps there. That's one of those that actually jump at you. All the rest are very, very good. And up here, they don't have salt waters into the clay. Why would they? But still, you can actually say we have a decrease in resistivity close to the clays. Now, the question is Can you actually differentiate between the clay and salt water potentially above the clay? Which is not an easy thing because they are in direct contact and both of them are conductive. So there is a very good correlation with salt water resistivity, and there is also good correlation with shallow clay layers. And conductivity does seem to extend above it in places, but it's very hard to pull them apart. So again, this is results without any sort of a priori. Again, you get a feeling here that this is actually coming from above the clay. But it's inconclusive until you start using a priori information. So, before we get there, also, so back up a second, I'm not getting into a priori yet. I just want to sample the model space even further to be able to say that this realization we're looking at is actually a fair realization of, a fair representation of all the models that can fit the data. So we actually went from a deterministic approach, just on one sounding, onto a Bayesian approach. So that specific sounding there has this result when it comes to just deterministic inversion. This is an MCMC, also ran using Orisynth, that basically tells us that, yes, what we're looking at here, what we're taking as the answer is actually a fair representation of majority of models that actually can fit the data. So once we get that out of the equation, we can actually start worrying about, adding a priori. So up till now, I haven't used a priori, so you look at it and you think, okay, what is the smartest way of using the ancillary information we have? We've got salinity concentration, we've got clay, and we've got these ERTs. Now, we're not going to use this resistivity information. It's too local. So it may give you some sort of hint somewhere, but we need to learn something about things over the entire area. And it's also resistivities and resistivities, so it wouldn't help much. I mean, once we're satisfied that the system is actually giving us resistivity that it should, we don't need to recalibrate anything in terms of resistivity, so we'll leave them alone. We're not interested in using salinity at this stage. The things that make the most sense is use that clay layer, which is very well defined, and they know from geology it should be everywhere and fairly flat. So we're going to use that because we want to answer the question, getting back to Ted's comment, what is the question that the client poses? The question is, can I see the salt water above the clay? We have the clay, let's try to pull that out. So we took that as a priori, and basically we tried to pile up all the conductance within these 4 meters, 2 to 4 meters. And basically the question that we posed to the data through the inversion is, can you fit the data having nothing conductive above that clay layer, and just put the conductivity there? And the answer is no, because this is the result without the a priori, this is the result with a priori. So basically, you can see that in places, for example here, and arguably you could say that it was, it was shakier here than there. So in here, you can almost, fit the data putting almost all the conductors in here. But in here, where also our results without a priori gave us a stronger hint that this was actually happening above the clay, we can't fit the data just having all the conductivity in there. If you really force it to put it just there, it doesn't fit the data. That's simple. The misfit goes through the roof, and that's a very clear indication. So you have to play with all the information you have. A model that doesn't fit the data, to me, actually carries more information than one that fits the data, because we all know that out of those that fit the data, we're just giving you one, and there's infinite that fit the data. Hopefully their spread is not big around the one that you're presenting, but it's equally important for the client to know if his prior knowledge can actually fit the data. And if it can't, and they accept it, they're very happy. They've achieved the goal. And we should play with this much more. So the answer is that we can't pile up all the conductivity just within this layer. So this is, again, the results without a priori over these 5 cross sections, and the next slide will be the results with a priori. So this is roughly where that a priori came in. It went to that. So I flip forth and back. So we went from there to there. And the conclusion is the same. There are places where we can be sure that there is something conductive above the clay. There are places where we just don't have sensitivity. It doesn't mean that it's not there, but we can't be sure that it's there. But there are places where we really are sure that it is there. How does this compare with groundwater salinity? So these are the results of a priori, and resistivity versus chloride just above the clay. This is how they show. Obviously, normally you plot conductivity versus chloride, not resistivity. I don't know why France did that. So you can't expect any straight correlation in here. On top of it, it's a log-log scale. So I'm not going to try to tell you what it should look like. It makes sense though. And the coloring is the depth. So all this stuff happens above the clays. This stuff happens at depth. But you know, the trend is correct. So to answer the original question, where is the wedge of conductive stuff? So we simply extracted the elevation of the conductive layer, and we used 5 meters. We tried different things, comparing ancillary information. We decided 5 meters was the most appropriate threshold to use, and basically we were able to outline this area. So this is saltwater sliding on top of the clays, and our data, smartly integrated with our ancillary information, proved to us that this is actually happening. Now, has this progressed in time? That's something that the client is looking at the moment. I don't have that answer, but they had this map from drilling or further back, and they're doing that. But our task finished at actually proving that this is salt water sitting above the clays. So the conclusion is that Airborne EM does very well at mapping seawater intrusion. We all know that. Otherwise, we wouldn't be here. However, you can have difficulties pulling apart, conductive layers that are in contact, unsurprisingly. The quantitative use of a priori can help a great deal, either because you put it into your inversion or because it tests scenarios. I can't stress that enough. Then the next question would be, okay, it's easy to do this in the Netherlands. You've got hundreds of holes per square kilometer. Can you apply that here? I think you can to some extent, because you always have some ancillary information. There always are a few holes. If not holes, you've got topography, you've got rhythm patterns, you've got your understanding of the genesis of the entire system, so you always know something about it. And it is all about testing hydrogeological concepts. Even if you had just one hole, you could test if that, what came out actually represents the results of the whole area. So this is it. Thank you.